All right, class, so this is another ALEKS topic. It's called calculating the pH of a weak acid titrated with a strong base. There's another very similar ALEKS topic that's called calculating the pH of a weak base titrated with a strong acid. And the concepts for both of them are going to be exactly the same. So we're just going to work through this one. I'm going to do two examples of this same problem because there's two sort of different versions that you're going to run into. This is probably the most common version you're going to run into. So I've got a chemical reaction here where I'm going to take butanoic acid with this chemical formula and I'm going to titrate it with KOH. And so the first thing you're always going to want to do is write out a balanced chemical equation. And I know that we don't do this very often. I know that it's maybe intimidating because you're not sure exactly how to do it, or you're worried that you're going to do it wrong. But the more you practice writing out these balanced chemical equations, the better you're going to get at it, and then the easier it's going to be, the more confidence you're going to have. Your skin's going to get better. Everything will be better. So definitely practice this. Work through these chemical reactions, and then it'll become easier and easier as you go. So anyhow, this is what I would start with. So I've written out my butanoic acid, this is my weak acid, and OH minus. So it's KOH, but we know that the potassium is going to be a spectator ion. Really the important part there is the OH minus. So this is going to react to give us H2O. It's going to be a neutralization reaction, and then we're going to form this conjugate base of my weak acid. So the next thing I would do is sort of gather the information, right? Sort of organize and figure out where I'm at and what I need to do. So the next thing I would do is I would take this information of, we're starting with 110.8 milliliters of a 0.4700 molar butanoic acid solution. And then for my KOH, or my OH minus source, I've got 0.8600 molar, and then I'm going to be adding 44.86 milliliters of that. So this is sort of, again, just organizing the information. I'm not trying to jump everything, do everything all at once. I'm just sort of taking the information down, organizing in a very easy way for me to sort of process, and then we're going to go through that process. So this is the starting point, and right away, if I see this, if I write out this balanced chemical equation, I'm going to say to myself, well, this is a reaction that's going to go to completion. This is a strong base that's going to drive this reaction to completion, and then I'm probably going to have to sort of say, well, what's left over, and then consider what's left over and how that's going to behave in the solution. So if this is my starting point, I would then say, well, if I'm going to run this reaction to completion, I need to know the number of moles of each of these things. So if I take these, molarities and volumes, I can convert those essentially to numbers of moles. So this is going to equal 0.05208 moles of butanoic acid is how much I'm starting with. And then I can do the same thing for my OH minus, and I'm going to be adding in 0.03858 moles of OH minus. That's how much OH minus I'm putting into that solution, right? So this is going to be stoichiometry. This is going to be a limiting reagent problem. I'm going to do a start and an end. So some of you might have looked at BRR tables for stoichiometry, beginning something I don't even know. I think that's silly. I think we can just look at, this is the starting amount that we're going to have. We can figure out what's the limiting reagent. We can do stoichiometry. That's something that you should just be able to do, right? You should just know how to do that at this point in your chemistry careers. I'm just going to ignore the water. And then initially for my weak base, I'm going to have 0 moles. So I can recognize this is a 1-to-1 reaction. So I can see that this OH minus, that's going to be my limiting reactant, right? Limiting. So after this reaction has gone to completion, I'm going to end up with 0 moles of OH minus. And since this is my limiting reactant, I can say, well, all of that's going to be reacted. And as this reacts in a 1-to-1-to-1 ratio, every time this HC3H7CO2 reacts with OH minus, I get 1 mole of this C3H7CO2 of the conjugate base. So if I run out of my OH minus, well, this amount of moles, it's all essentially going to be converted to my weak base. So I know that I'm going to have 0.03858 moles of my weak base. And again, that's just stoichiometry. I'm doing a limiting reagent problem. This is my limiting reagent, how much it's going to be produced as I move from left to right. Now, for my weak acid, I'm going to be consuming some of this, right? But there's going to be some left over. And the amount that's left over is going to be 0.05208 minus however much OH minus I used up, right? How much was consumed. So at the end of this reaction, I'm going to end up with 0.013496 moles of that acid. So I'm carrying a lot of digits here. We'll do all of our rounding at the very end. It's the best way to sort of make sure that we've got the right answer, is to carry a bunch of digits, and then at the end we'll sort of figure out what we need to do. Now the other piece of this puzzle is I've got a new total volume. So I'm mixing these solutions together, right? So if I have my beaker here, I'm going to start with 110.8 milliliters, and then I'm going to add in 44.86 milliliters. So I've my new total volume here is going to be volume total equals 155.66 milliliters. So that's another thing to keep in mind as I'm mixing these things together. Okay, so the next step here is to essentially say, well, what do I have now? What's going on in the solution? And what's going on now is I've got this weak acid with some certain number of moles, and I've got a weak base. So what I've made here is a buffer solution. I have a buffer now. I've got some conjugate base and I've got some conjugate acid, so this is a buffer. So what I would recommend doing next is using the Henderson-Hasselbalch equation. pH equals pKa plus log of the concentration of base over the concentration of acid. Keep in mind that these are supposed to be concentrations. We can get away with some shortcuts here, but I'm not going to do that. And if I want to put in my concentration of base, my concentration of acid, I'm going to convert my number of moles into molarities using my total volume. So this is my number of moles divided by my total liters, right? Total liters over here. So this is going to end up being 0.248 molar in my weak base. I can do the same thing for my conjugate acid. So that would equal, where'd it go? 0.0867 molar in my conjugate acid. So now I've got all the pieces I need to actually solve for the pH using the Henderson-Hasselbalch equation. So for my pH here, that should equal, I've been given the pKa, 4.82, plus the log of the concentration of the base. So this one is my base, 0.248, over the concentration of my acid, 0.0867. Plug this in, solve for my pH, and that should give me a pH equal to 5, let's make sure you guys can see, 5.27. So that should be my answer. Answer to 2 decimal places. I can round that at the very end there. So that is the most common way that you're going to see this problem. We're going to be somewhere, between the start and the equivalence point. So that becomes a buffer, and we can use the Henderson-Hasselbalch equation to solve that problem there. All right, so the other way that we're going to see this problem is like this. So here's just a very similar type problem. We're going to be starting with this cyanic acid, HCNO, adding, again, KOH. I've sort of set the problem up like this already. And now what I see is when I start here, so this would be my starting point for my reaction that's going to completion, right? I'm gonna run this reaction to completion because I've got this presence of strong base. And then I'll sort of say, okay, what's left over in the solution? How do I, treat that? Is it a buffer? Is it a, is it at the equivalence point? And I just treat this. Is it past the equivalence point? And that's where we're gonna be here. Because in this case, my HCN, my weak acid, is my limiting reagent. So after this reaction goes to completion, I'm going to have used up all of that weak acid. So that's going to be 0 moles for my HCNO. And then my OH minus, there's going to be some left over. 0.111 minus this value here is going to say that there's 0.01405 moles of OH minus left over, and that's strong base, and that strong base that's left over. We can figure out how many moles of CNO are formed. It doesn't really matter in this case, but it will be 0.0971. It will be the same as my limiting reactant, but because we have leftover OH minus, this is really going to depend or determine what the pH of my total solution is. Again, I'll want to know what the total volume is, just like last time. So the total volume in this case is going to be 306.3 milliliters, so just adding up the volumes that I'm mixing together. And with this total number of moles of OH minus left over and this total volume, I can figure out the concentration of the OH minus. Concentration of OH minus, that will equal 0.01405 moles of OH minus that are left over. Divide that by 0.3063 liters. and that gives me a concentration of 0.04587 molar. If that's my concentration of strong base, then I can use that to calculate the pH. So pOH will equal 1.33, and then pH will equal 12.66. That is my answer. 2 decimal places, 2 decimal places. So this, we do not need to have any ice table. We should not have any ice table. And it's just going to be sort of stoichiometry. And then since I've got leftover strong base, that's going to be what determines my pH in my solution. Okay.